Hi friends, so welcome to lecture 54 of my helicopter dynamics class, and today we are going to use some of the expressions I derived previously for the blade section forces to get the rotor forces. So these are the composite or combined forces which are acting on the rotor. I am Dr. Ranjan Ganguly. Now when we look at the rotor, we have derived expressions for the forces which act at any blade section, and we have named these forces as Fz, which is vertical, Fx, which is like a drag force, and Fr, which is a radial force. And now what we do is we look at the entire rotor as a system and we try to get expressions for the forces which act on the entire rotor. So we are going to see a couple of forces. One is the H force, which is the rotor drag, which is backward. So velocity of the rotor is coming from here, and then this is the drag. There's also a rotor side force Y which acts towards the right here. Now beside these two there is also the rotor thrust, which is of course vertical, and there is a rotor torque. So all these four forces are very important and we need to derive expressions for these. So let's start with the rotor thrust. So the rotor thrust T can be given by this expression here. Now to understand these expressions we look at the two main parts. One is you are taking the Fz, which is a sectional load or a sectional force which acts vertically. You're multiplying it by the length dr of this section and then integrating from 0 to r, where r is the radius of the blade. So that would be the force generated by the entire blade. Now there are n blades, so we need to sum this from m is 1 to n. So let's say if there are 4 blades, then we have to take the total force being generated by the 4 blades. If there are 5 blades, then we have to take the force generated by the 5 blades and so on. So this is how BET lets you calculate the rotor thrust. The next important expression we need is for the rotor torque. And so to get the torque, we need to realize that torque is in plane in the rotor disc system. And therefore we take the force Fx, which is like a drag which acts on the section. And then we multiply this force by the radial arm, which is small r, which is the distance from the root to the current section you are in. So that is r into Fx. And then we multiply it by the small distance dr, which is the sectional length. Then we take this expression and integrate it from 0 to capital R, where capital R is the blade radius. Now there are n blades, so again we need to sum this from m is 1 to n to get the torque of the entire rotor as predicted by BET. So now you can start seeing the advantage of obtaining these terms Fx, Fz, Fr and so on, which we did in the previous lectures. So now we turn to the rotor drag, which is H, which is in this direction. And here we now need to resolve these forces. So if you see here, H would have two components. There would be a component coming from Fx and there would be a component coming from Fr, because Fz is vertical. That's not in the plane of H. So if we resolve these components, we see that we'll have to multiply Fx by sine of psi, because psi is this angle. So this is going to be 90 minus psi. So Fx cos of 90 minus psi would be the force into sine psi. Similarly, we'll take the force Fr and we multiply it by cos psi. So that gives us the component in this direction. So essentially we take this particular equation here. These are the components of the forces in the direction of H. We multiply it by dr and then integrate it from 0 to r, where r is the radius of the blade. And then because there are m blades, we need to sum it on the n blades here. So m is 1 to n. Now remember that psi m here is the angle correspond to blade number M. Okay, so there are going to be several blades here. One blade may be here, one blade may be here, one blade may be here. So the connectivity between all of these would be that this plate, the size would be different. There would be the starting size plus some radians and so on. So you need to calculate that based on the number of blades which are there across the rotor disc. So now we turn to the final rotor force Y. And so again, to get Y, which is on the side force direction, we need to take the forces and resolve it along the Y direction. Now again, recall that Fz is acting vertically, so that doesn't come into play. So I need to resolve Fx and Fr. So here the component of the Fr radial force would be in this direction, so that would be sine. So I will take Fr and multiply it by sine psi. And as far as Fx is concerned, that's a negative force because it's acting in the reverse direction of what we have given as y here. So that would be into cos, and there would be a negative sign here. Okay, so that would be the expression for the force in the y direction, and then again we multiply it by dr, which is a small length of this section here. We integrate it from 0 to r across the entire rotor blade, and we sum it from m is 1 to n for all the n blades which are there. So this way you can get the rotor forces, the thrust and the torque, given you have obtained expression for the sectional forces using the BET. So this is how you really perform the calculations here. You use BET to get the sectional forces in terms of CL and CD for the particular blade section. So you use the two-dimensional sectional properties. Then the rest of it is simply basic mechanics, Newton's laws and so on. You resolve the forces, you integrate the forces, and you sum them across all of the blades. So once we have done that, we get the rotor forces. So in the next class, I'm going to discuss about the blade flapping equation in forward flight. So we are going to return to flapping equation, but the right hand side is now going to get very complicated because we are going to have all the forcing terms which are now periodic terms. See you then.